That passage from Mozart's 40th Symphony is so remarkable because Mozart manages to construct a melody out of the 12 notes of the Western musical scale without repeating the same note twice. For that reason, it reminds me of the named distribution we'll study in this video, the hypergeometric distribution, which involves drawing without replacement from a box. So once a ticket has been drawn, it's gone forever. It can't be drawn again. In other words, you can't draw the same ticket twice. Just as Mozart challenged himself to not repeat the same note twice in the passage we just heard. Here's how the hypergeometric distribution is defined. Like with the binomial distribution, we start off with a box of tickets. Some of the tickets are labeled 1, the rest are labeled 0. Then, we're going to draw little n tickets without replacement from this box. So we'll end up with little n tickets, some are zeros, some are ones. And the hypergeometric random variable is the number of 1 tickets we get in our sample of size little n. So the only difference between the binomial and hypergeometric distributions is whether you're drawing from the box with or without replacement. Once you identify a random variable as having a hypergeometric distribution, you can simply write down its PMF, which is given by the following formula. Notice how the PMF depends on the parameters n1, n0, and little n, and is a function of x. So the possible values of this random variable usually are 0 to n. Now there are some exceptions. For example, if you only had 4 ones in the box, but you were drawing 6 times without replacement, well, you wouldn't be able to get up to 6 ones. You'd be able to only get at most 4 ones. Now, what would go wrong if you tried to plug in 6 for x in this formula, but there were only 4 ones? Well, this combination would be 4 choose 6. And if you try to expand that in terms of factorials, you'd end up with a negative factorial. So let's just assume that anytime you're choosing more things than there actually are, the number of ways to do that is 0 by definition. Now, notice that the hypergeometric distribution has 3 parameters. You might recall that with the binomial distribution, we were able to reduce the number of parameters from 3 to 2. We argued that because we were drawing with replacement, it didn't matter exactly how many ones and zeros we had in the box. All that mattered was the relative proportion of ones and zeros. So we were able to parameterize it in terms of just n and p, which is the fraction of tickets that are ones. However, with the hypergeometric, we can't parameterize it in terms of just n and p. Because the draws are made without replacement, it matters how many ones and zeros we start with. Let's look at some examples of hypergeometric random variables. First, let's consider the number of aces in a 5-card hand dealt from a standard deck of cards. Now, why does this random variable have a hypergeometric distribution? Well, let's draw out the box model. So I'll have a box, and in this box, I'll put 52 tickets, representing the 52 cards in a deck of cards. Now, I'm only interested in the number of aces for this problem. So I don't really care about exactly what card each one is. All I care about is whether it's an ace or it's not. So there are 4 aces, and the rest of the cards are not aces. So I'll represent them by an X. So we have 4 aces, and we have 48 non-aces. Now, to represent the 5-card hand that I get, I'm going to draw tickets without replacement. Draw 5 tickets without replacement, because in a 5-card hand, I can't have the same card twice. That's why it's without replacement, and that's why it's going to be hypergeometric. Now, how do I label each of these tickets? I have to label them with ones and zeros. Well, the hypergeometric random variable is going to be the number of ones. I'm interested in the number of aces, so I'll have the aces be ones, and the rest of the tickets be zeros. So now, I've completely set up the box model, so we can see that this is going to be a hypergeometric random variable with 5 draws from a box with 4 ones and 48 zeros. Let's do another example together. Suppose we're going to form a 21-person Senate committee at random from the 100 US senators, and we want to know how many Republicans are on this committee. Now, why does this random variable have a hypergeometric distribution? Well, let's set up the box model to see. So in my box, I'm going to put 100 tickets representing the 100 US senators. And I don't really care about who they are exactly. All I care about is whether they caucus with the Republicans or the Democrats. So I'll label each of these tickets with either a D or an R. So D for Democrat, I know I have 49 of these, and R for Republican, and I know I have 51 of those to begin with. Now I want to form a committee of 21 people, and the same person can't be on the committee twice, so I need to draw 21 tickets without replacement to ensure that I get 21 distinct senators. And since it's without replacement, that's where the hypergeometric distribution is going to come in. Now, since we're interested in the number of Republicans, we should let Republicans be ones and Democrats be zeros. So now the number of ones in those 21 tickets will represent the number of Republicans on the committee, and that, we know, has a hypergeometric distribution with 21 draws from a box containing 51 ones and 49 zeros. Now, let me leave you with another passage, this one by J.S. Bach, that also features a melody constructed without replacement from the 12 notes of the Western musical scale.